Okay, let's continue on with this one now. It's a bit complicated. You'll see that we had two equations, two unknowns. Hopefully with what we've done here by substituting the negative 4 over 5 over r to the 4 into this equation, we can simplify it and potentially solve for something. So if I look over here, I have r to the 4th power. Sorry, let me use a different color here. I have r to the 4th power in the denominator, r to the 15 in the numerator. So using my exponent laws, r to the 15 over r to the 4, I can subtract the exponents. So my negative 405 is still hanging around there, but subtracting the exponents there, r to the 15 over r to the 4 gives me r to the 11. So I still have the 71 million stuff over here on the left. But now this is an equation that I only have one variable and I should be able to solve. So I'm going to divide both sides of the equation by negative 405. Okay, and let's see what that gives me. So that gives me negative 177,147 on the left, and r to the 11 on the right. And I should be able to solve this by taking the 11th root of both sides. So if I take the 11th root of that, that should be equal to r. So that gives me r being negative 3. Okay, so again, a little bit complicated, but I was eventually able to get the right answer. So once I have that, now that I have r, I can solve for whatever else I want. If I want to solve for a, I can use this original equation right here. So I'm going to have negative 405 equals a times negative 3 to the exponent 4. So negative 3 to the exponent 4 is 81. I have 81a. So divide both sides by 81 to solve for a, I get negative 5. So that tells me my first term is negative 5, my common ratio is negative 3. So I can get my general term now by subbing both of those into the equation. So a is negative 5, r is negative 3. And I have my general term. Okay, once I have that, I can quickly find out my first three terms. So for my first three terms, I already discovered down here that my a was negative 5. Okay, if my r is negative 3, I'm going to multiply that by negative 3. So negative 5 times negative 3 is positive 15. And then to get my next term, 15 times negative 3 is negative 45. So there are my first three terms of the sequence, and now I've solved part B as well. Okay, so again, a little bit tricky. I had to solve a system there, but again, using the idea of substitution, I can isolate for a variable, sub it into the other equation, and get my answer from there. Okay, so number 6, it's a little bit weird. It says determine the 10th term of the sequence 3, 15, ... we don't know what else. What's tricky about this one is you can actually interpret this multiple different ways. If I wanted to see this as geometric, I'd be multiplying by 5 to get from one term to the next, but there's no third or fourth terms here for me to actually establish the pattern. I only have 2 terms here. It's not enough to establish a pattern. If I wanted to treat this as arithmetic, I could by saying I would be adding 12 to go from one term to the next. Or it could be some other sequence entirely. It could be neither geometric nor arithmetic. So right now there's not enough information for us to establish a pattern to get a general term. But let's just say we wanted to approach this one and do this using one of the patterns we've known so far. We could treat this as being either arithmetic or geometric and find the 10th term that way. So if it was arithmetic, you would have an a value of 3 and a common difference of 12. And if it was geometric, you'd have an a value of 3, but you'd have a common ratio of 5. Okay, so I'll have you guys do this on your own just as a bit of a practice here. Find the general term for each of these, whether it's arithmetic or geometric, and then tell me what the 10th term is. Okay, so give it a try, push play, and ready to go through it together. Okay, so there are your answers. So hopefully you found the arithmetic and geometric general terms for each case. When you get general terms, so the arithmetic one's there, the geometric one's there. You sub 10 in for n, and then just solve for your 10th term. Okay, one last example. So I want you to find the general term of this sequence right here. So play around with it a bit, see if you can find the pattern that goes from one term to the next. Now remember, I didn't say if it was arithmetic or geometric, so that's up to you to try and figure out. And again, see if you can figure it out, and push play and go through it together. So the first thing you might have noticed here is that if you're trying to see if it's geometric, it's not a common ratio, right? If you do 5 over 6 divided by 2/3, so the second term divided by the first term, you wind up with about 5 over 4. But that's not the same thing you get if you take the third term and divide it by the second term. So 2/3 divided by 5 over 6, well, it's going to be 4 over 5. Okay, and it seems kind of weird here. I mean, your first term and your third term are the same, right? So there's no real common ratio that could work. So this one is not geometric, so that doesn't work. And it's clearly not going to be arithmetic either, because even if you're going up from 2/3 to 5 over 6, it goes back down to 2 over 3 after that. So this is neither arithmetic or geometric right now, and so it's a little bit tricky to find the pattern. So one thing that might be helpful here is try rewriting some of the fractions here using equivalent fractions, but that might help you see the pattern a little bit easier. So what I mean is, for example, if you look at the second 2/3 here, let's see what happens if we write that as 8 over 12. Okay, so we have, again, 2/3, 5 over 6, we have 2/3, 8 over 12, so it's an equivalent fraction, but hopefully you can see a bit more of a pattern now, and 11 over 24. What you're going to notice here, or hopefully what you might notice, if you look at the numerators only, the numerators go 2, 5, 8, 11. Okay, so if you look at the numerators, you're starting at 2 and going up by 3 every single time. Okay, so the numerators seem to follow an arithmetic pattern, or an arithmetic sequence, I should say. Okay, if you look at the denominators go 3, 6, 12, 24, ... And hopefully you see that these, you're multiplying by 2 every single time. So the denominator actually follows a geometric pattern, or a geometric sequence. So it's a little weird, but you can actually have a different general term for the numerator as you do for the denominator, a different pattern. So what we can actually do is treat the numerators and denominators separately, find a general term for the numerator, find a general term for the denominator, and put them together to find an overall general term. Okay, so let's do that here. Let's do it one at a time. Let's deal with the numerators first. So I'm just dealing with the numerators here. I'm going to have an a value of 2, a common difference of 3. So Tn is going to be a, which is 2, plus 3 times n minus 1. So that's going to give me 2 plus 3n minus 3, which simplifies into 3n minus 1. So this is a general term for the numerator. Now I'm going to do the exact same thing for the denominator. So my denominator again was 3, 6, 12, 24. So that gives me an a value of 3 and a common ratio of 2. So that means my general term, a is 3, r is 2, so 3 times 2 to the n minus 1. And that'll be my general term for the denominator. Okay, so I can now put everything together into one big general term for the entire sequence. So for my numerator, the general term is 3n minus 1. For the denominator, my general term is 3 times 2 to the n minus 1. And this will be the general term for my ugly sequence up here. Okay, so again, it looked kind of weird. It was neither arithmetic nor geometric, but we were able to find patterns in the different parts of the fractions to create an overall general term. Okay, that one is a little bit trickier. Okay, so that's it. Again, in your homework, if you see anything involving the word recursive form, the recursive definition, ignore it for now. That's actually going to be covered in our next lesson. So don't worry about it right now. We'll do it in next homework. Okay, that's it. That's all.